Okay, I welcome you all to my video lecture presentation. Myself, C. Ashok Kumar, a professor, Department of EEE, MLR IT. And my course name is Electronic Device and Circuits. And it is Unit 2, name is Diode Applications. And the topic for today video lecture is Inductive Filter Operation and Derivation of its Ripple Factor. And the overview of my presentation goes on like this. First, I will be explaining about the operation of the inductive filter, Fourier rectifier with inductive filter, and then I will be deriving the ripple factor of the Fourier rectifier with inductive filter, and I will be finally recapping the things whatever I discussed. And these are the textbooks referred. And first of all, let me introduce about the action of a filter. Why you go for a filter? Filter, if you observe the full wave rectifier output, it will be like this. It is a pulsating DC. As you can see here, this is output voltage with respect to time. As you can see here, it is looking like a pulsating DC. The meaning here is it contains both AC components plus DC components, but the rectifier output must be a pure DC like this. But here what is happening, it is a pulsating DC. The meaning here is pulsating DC means it is a combination of both AC components and DC components. I want to minimize the AC components. Why? Because I need to obtain the output voltage like this, which must contain only the DC components. So that's why I need a device which minimizes the AC components. That's why here we will be making use of filters. The last class I discussed about the capacitive filter, how we are minimizing the AC ripples. And here one more type of filter, we are using the inductive filter. As you can see here, this is a filter, inductive filter. Always it is connected to the load resistance in series. Okay, whereas if you take the capacitive filter, it will be connected in parallel with the load resistance. As you can see here a full wave rectifier circuit will be there, and here I am connecting a inductive filter here, which is in series with RL. Okay, so how the action of this particular inductive filter goes is, as you can see, first of all, the operation of inductive filter depends on its well-known fundamental property to oppose any change of current passing through it. Okay, so it opposes any change of alternating current like this. As you can see here the full wave rectified output contains both AC and DC components, and whenever the AC component is made to allow through this inductive filter, what happens here? It opposes. That means it acts like a open circuit. That means it won't allow the AC current to pass through the load resistance RL. Okay, so whenever DC current is allowed to pass through the inductive filter, it allows, and so here only a DC current will flow. So that's why the output voltage will be a DC voltage. So this is the action of the inductive filter. Mainly it opposes any change of current passing through it. That means it acts like a short circuit to DC component, and it acts like a open circuit for AC component. Okay. So finally, if you go for the calculation of ripple factor, you will be getting the ripple factor as RL by 3 root 2 omega. That will be seen later. So if you observe the full wave rectified output, will be like this, as I said. So this is 0, this is pi, and this is 2 pi, and so on, and this is omega t, and here this is V naught, and here this is the peak value, let it be Vm, V suffix m, okay, peak value. So if you go for the Fourier series representation of this particular wave, which is a full wave rectified wave, okay, so by given data, So 0 to pi, the magnitude is Vm. From pi to 2 pi, once again it is Vm. Okay. So if you go for the calculation of the Fourier series, you'll be getting this equation. So if you write this particular full wave rectified output wave by making use of full Fourier series, the equation will be like this. As you can see here, so it is a combination of both. It is a combination of both DC components as well as AC components. As you can see here, this first term. The first term is 2 Vm by pi. This represents the DC voltage. And as you can see here, remaining higher order terms, as you can see, next term is minus 4 Vm by pi into 1 by 3 cos 2 omega t. That means it is a AC voltage. AC voltage and the harmonic is 2 omega, right? And the next term minus 4 Vm by pi into 1 by 15 cos 4 omega t. That means once again it is a AC voltage with a harmonic of 4 omega and so on like this. So the first term is the DC voltage term and the remaining terms are related with the AC voltage terms at different harmonics. Okay. Harmonic means here 2 omega, 4 omega and so on like that. Okay. So this is a voltage equation, full wave rectified output voltage equation, right? And from this voltage, if you want to write the current, Im is equal to the peak value of current is equal to peak value of voltage Vm by RL, where RL is a load resistance. As you can see here, the load resistance here is it is a combination of both. As you can see, it is a combination of this inductance as well as RL. If you go for the impedance can be written as RL plus J omega L. Okay, so this is RL, resistive component, and this is the inductive component. That's why if you write the impedance Z is equal to RL plus J omega L. So that's why here while calculating the current here, Im is equal to Vm by RL. So before going into it, the impedance of series combination of RL and L at second harmonic. Why? Because here second harmonic voltage value is known to us. So that's why here I am taking the second harmonic. That's why the impedance can be written as impedance of the combination of both L and RL can be written as root over magnitude here, root over RL square plus 2 omega whole square. Okay, these are magnitude of impedance. Generally impedance is RL plus J 2 omega L. So if you write its magnitude, root over RL square plus 2 omega L whole square. So this can be written as root over RL square plus 4 omega square L square. Okay. So for AC component, how to calculate Im? Im is equal to Vm by the impedance magnitude, that is RL square plus 4 omega square L square. So this is for AC component. Current AC component can be represented like this. Im is equal to Vm by Z, where Z is equal to this one. Okay. So total current. So here we know the voltage equation. We are writing now the total resulting current by considering only the second harmonic, and here I am ignoring the higher order terms related with higher harmonics. So we are considering only for 2 omega. Okay. So that's why here. So first term, what is the current term here? So here the voltage is 2 Vm by pi. So if you want to calculate the current Vm by RL, so that's why here 2 Vm by pi into 1 by RL. Okay. So this is related with the DC current term. Okay. Next is AC current. As you can see here. So this is the magnitude here is 4 Vm by pi into 1 by 3. 4 Vm by pi into 1 by 3. So 4 Vm by pi into 1 by 3 by ZL. ZL means RL square plus 4 omega square L square. Okay. Cos 2 omega t minus 5. Why? Because it is a AC component, a sinusoidal representation. That's why cos of 2 omega t minus 5. Okay. Where phi is the angle. So next we need to, main objective for us is we need to calculate the ripple factor. Ripple factor is, this can be written as VAC by VDC. Okay, it is the ratio of RMS value of ripple. RMS value of ripple. Ripple means here, ripple means AC component. RMS value of AC component by DC value of the wave. Okay, RMS value of AC component. So here 4 Vm by 3 pi. So this is peak value. If you want to write the RMS value, RMS VRMS is equal to Vm by root 2. This is a basic equation. If you know the peak value, if you want to write the RMS value, VRMS is equal to Vm by root 2. So Vm, already we know the value as Vm as 4 Vm by 3 pi root over RL square plus 4 omega square L square into 1 by root 2. So as you can see here, Vm by root 2, that root 2 here. Okay, and this is about RMS value of AC component, and the denominator is the DC current. DC current means, as you can see here, DC current means this one, 2 Vm by pi RL. Okay, so ripple factor is equal to RMS value of AC voltage by DC voltage. That simply we can write it as VAC by VDC. So this is RMS value of AC component, and this is the DC component 2 Vm by pi RL. So this is related with the current. Kindly keep in mind, this is not related with the voltage, right? So we converted the voltage into current. Okay, so we'll be getting 2 by 3 root 2 into 1 by root over 1 plus 4 omega square L square by RL square, right? So normally omega L by R, always it will be very, very large when compared with 1. So that's why here 4 omega square L square by RL square is very, very larger than 1. So if you observe this term, when you compared with 1, it is very, very large. So we can ignore this one. So if you ignore this one, the ripple factor is equal to RL by 3 root 2 omega. Okay, and this will be root 2 by. Okay, so tau is equal to, you will be getting, and here this one, whenever it is ignored, you will be getting 4 omega square L square by RL square under root, that means 2 omega L by RL. So whenever you remove this square root, you will be getting 2, and finally you will be getting a simplified version like this. Tau is equal to RL by 3 root 2 omega L. Okay, so this is a ripple factor. By this ripple factor, we can conclude two conclusions. So always the ripple factor, we need to minimize the ripple factor for the better performance of the rectifier with the filter, right? So if you want to minimize the ripple factor, so whenever if you want to decrease this ripple factor, what are the ways here? You need to decrease the value of RL. Okay, first option is we need to decrease RL. Okay, whenever you are decreasing RL, we can decrease the ripple factor. And what is the other way to decrease? As you can see here, this ripple factor is inversely proportional to L, where L is the inductance of inductive filter. So it is inversely proportional, means if you increase the value of the L, we can decrease the value of ripple factor. Okay, so finally I can say that if I want to minimize the ripple factor of full wave rectifier with inductive filter, first option is I need to decrease the value of load resistance RL, and second option for me is I need to increase the value of inductance. Okay, so in this way we can minimize the ripple factor. So finally the ripple factor equation is RL by 3 root 2 omega L, where omega is equal to 2 pi f. Okay, where f is the frequency of operation, right? So based on this particular derived equation, the problem will be asked like this. Okay, these are given data based on the ripple factor. A problem is there. These are given data. Calculate the value of inductance to use in inductive filter connected to a full wave rectifier. It is an inductive filter connected to a full wave rectifier operating at 60 Hz Operating at 60 Hz means the given data here is f is equal to 60, frequency of operation. And a DC, provide a DC output with 4% ripple per 100 ohms load. 4% ripple. Ripple factor is also given in terms of percentage. So 4 by 100 means what is the value here? 4 by 100 means 0.04. So that's why here the ripple factor value is given as 0.04. Ripple factor value is given, frequency of operation is given, and here also is saying load, 100 ohms load. That means RL value is given. RL value is given as 100 ohms. Okay. So first you write the formula here. The formula here is the ripple factor is equal to tau is equal to RL by 3 root 2 omega L. Okay. So what is the given data here? RL is given, omega is given, and tau is given. We need to obtain the value of L. Okay. So omega, the ripple factor value is 0.04 given data, and here RL value is given as 100 ohms, that's why 100 here, by 3 root 2 omega is written as 2 pi f. So 2 pi into f means 60 Hz into L. So L will be evaluated like this. L is equal to 0.0625 by 0.04. You will be getting 1.5625 henries. The units of inductance are henries. Okay. So in this way the problems may be asked based on the ripple factor. So this is about the ripple factor. Inductive filter, whenever you place inductive filter or a full wave rectifier, the ripple factor is derived here. And how to minimize the ripple factor means we minimize the load resistance RL, and second option is we need to increase the value of inductance of inductive filter. Okay, by this let me recap the things. So first I explained about the operation of inductive filter. What is the property of inductive filter, and what is the operation of inductive filter? Whenever you place inductive filter in series with the load resistance of full wave rectifier, what happens inside the device? Okay, how it is minimizing the AC components, how it is maximizing the DC output. Okay, so next we derived the ripple factor. So ripple factor, the formula is tau is equal to VRRMS by VDC. VRRMS means RMS value of AC components by DC voltage. So this can be simply, it can be written as VAC by VDC. Okay. So finally we derived the ripple factor, and we concluded by making use of ripple factor equation how to minimize the ripple factor, and then a problem was done based on the ripple factor. Okay, with this I conclude my video lecture on this particular topic. Thank you.